Hello, everyone. My name is Saif, and we're here to present about the life and death of kernel object abuse. I work as a senior security software engineer at MSRC, and this is Ian.
Hey, my name is Ian Kronquist. I work at Microsoft in the Windows Device Group, and I design mitigations.
So I like to think that there is definitely a method to any madness, and that I like to answer 3 specific questions about any problem that I'm facing. Is the why, the what, and the how. And that will get us to a point where we can fully understand the problem, and then we'll be able to fix it. If we look at recent attack trends, specifically towards elevation of privileged attacks against the Windows kernel, it usually starts by triggering some exploitable bug, like a use after free, out of bounds write, or an integer overflow. And then we try to gain a higher memory exploit primitive by abusing certain object types that allows for arbitrary kernel memory read and write. And from that point onwards, we use arbitrary kernel memory read and write to actually steal a system process token and assign it to ourselves or a newly instantiated process, thus gaining an elevated kind of privileges. Which brings us to the question of what? How actually do we get to that step and the first step of the chain? We're going to start by moving slowly through the memory corruption or use after free vulnerability and explaining what it is, how we usually would exploit it, and then move on to the other parts of the attack chain. If we look at the pseudocode in front of us, this is just a sample code. It's not a real world code or anything. It's just to explain the concept itself of use after free. At some point, the function will allocate an object. We'll call it object A. And within a certain condition, something will happen and the object will be freed. When the object is freed, the function later on works on an object member, which is object member B, tries to assign a value to it. When that happens, we'll actually get some memory corruption primitive because it's working on freed memory. How we would exploit this is by actually allocating a new object that is of the same size and allocated to the same heap that the previous object was allocated to just before the object was, after the object was freed. And then if we assume that the third object, which is object C, has the value of 1 for some member, then when we use the dangling pointer from the freed object and assign a new value to it, we're actually corrupting the object C's member. And thus, when we try to print it, it will have a different value that it usually is. So this is just an example of how use after free might work. So what we're aiming for is usually to find certain specific objects with specific members that are interesting to us, that has adverse effects, that when we use this memory corruption primitive, we change a specific value that will give us something much more interesting than just printing a new value. The next type of memory corruption that I like to talk to is x86 integer overflows. Oh, wow. So if you look at this calculation in x86 systems or 32-bit based systems, you'll realize that FF80 plus 81 will result in 1. Well, actually, this is wrong. The calculation results in 0100000001. But since it's a 32-bit system and this is 4 bytes wide registers, this value or this number cannot actually fit in a 32-bit register. So what happens is that the application of the processor will truncate the most significant byte, resulting in 1, and this what we call is integer wrapping or integer overflows. So this can have adverse effects, most specifically is in linear overflows. So if we have 2 scenarios, the first one is that we allocate an object based on a size that had some calculations on it that resulted in the integer wrapping from a large value to a smaller one. And the second scenario is that we allocate a fixed size object to memory. The next step is that the data copying step. In the first scenario, we copy using the original size before the integer wrapped around and the overflow happened, thus overflowing the memory adjacent to it. And in the second scenario, we're using a user-supplied value to copy data without checking that actually it is equal or less to the object size that was allocated. At that case, we will overflow the memory that is adjacent to the object in memory, which is the linear overflow part of it. The next part is about out-of-bounds write. So again, an allocation happens that is using an overflowed size, resulting in a very small size allocation. And then the function, or through the function, it's trying to write to a specific index of the object without checking that this index is actually bigger or larger than the allocated object size, resulting in an out-of-bounds write into the adjacent memory, depending on the index where it will go through. So how would we exploit out-of-bounds write or overflows is by getting the kernel memory in the deterministic states, and that happens by a series of allocations and deallocations. And then we create memory holes between user-controlled objects. Hopefully, the vulnerable object will be allocated into one of these holes and before a user-controlled object, and then use the overflow or the out-of-bound write to actually corrupt interesting members of the user-controlled object. And that brings us to the how. So after we got the memory corruption primitive and after we got our bug working, at that point we're only crashing the system or just like getting the system kernel memory in an undeterministic state, usually resulting in a blue screen of death. And as I mentioned, in case of use after free or out of bounds write or overflows, we need to get some user controlled objects in there, and these user objects needs to be interesting objects. And by interesting, I mean that they have interesting members and interesting functions. One of the most interesting members is the size member, which allows relative read and write. If you think about it, if an object has a size and you overflow that size or change its value from 1 to 100, it means that when you're working on that object later on, this value, it thinks that its size is 100, while actually its size is 1, accessing memory relative to its location in memory, and thus the name relative memory read and write. The next one is a pointer to data. So if that object has a data pointer member to it, that a pointer that points to certain location in the kernel memory for a string or for any kind of data like bitmap bits or something, you can override this pointer, then whenever you're reading and writing from that object, you'll be able to actually read and write from any controlled memory location, thus arbitrary read and write. And then it's the data itself, of course, and the object has to have interesting functions, which is functions that allow us to read or write data from it, like get data or set data. So this is the basic concept of what an interesting object constitutes for us. Next, we're going to talk about the theory itself of how object abuse works. So if we look at the slides and we think the first step is that we allocated two objects that had the data size of 100. Then we have an exploit or a bug, one of the bugs that we explained before, that would corrupt the size member of the object, making it to max int or 4 GB in that case. That means that when we're working on that object, trying to read data from it, we're actually able to write up to 4 GB from the data pointer of that object, which allows us to access memory that otherwise we wouldn't have access to. The next step is that we will use the initial object, the first one that we have relative and read and write for, to set the second object's data pointer to whatever, actually whatever pointer that we want. In that case, we have it 41, 41, 41, 41. And that means that whenever we try to read or do any operations from that object, we will actually be reading from a controlled memory location, and that usually is a kernel memory, and that we were looking for a certain process token or a certain interesting value in memory that we can abuse. So now we move on to talk about kernel memory. So there are three types of memories that, or I like to call them three types of memory in the kernel. There's the desktop heap, which contains the anti-user stuff. This usually contains window management related objects, and like these objects are windows, menus, classes, and such. Usually objects are allocated and free to that specific heap using RTL allocate heap or RTL free heap. The next one is the page session pool, which has we dubbed it anti-GDI, which contains GDI related objects, and that contains bitmaps, palettes, brushes, DCs, lines, and regions. Like the thing that I have to say here, that most people think that these objects, since you call it from user mode, are actually allocated in user mode, but in fact they're actually allocated in kernel. And these objects are usually allocated and freed using xallocate pool with tag and xfree pool with tag. There is also the non-page session pool, but this is not in scope for this presentation since we're not covering it in our mitigation. These are just some statistics of the number of cases that MSRC have seen so far in relation to specifically use after free vulnerabilities about these specific objects. The surface object is our bitmap. The tag wind is a window structure. As you can see, there is a many number of cases that appeared for MSRC or was seen by MSRC that had this objects being abused. And we're going to discuss these objects in details in the next slides. So we're going to start with the most oldest one and the most common one that was being used before, which was the tag window structure. If we look at the tag window structure in memory, you'll notice that it has specific interesting functions that I highlighted. So the CBWind extra member is actually the number of extra bytes that is allocated to the window. So if you're able to corrupt that, you're probably getting relative read and write. You have a buffer pointer that points to the window string name, which if you were able to corrupt it, you'll gain arbitrary read and write. And the highlighted in green part is the extra byte location in memory that you'll be able to read and write from. Now, it is worth mentioning that there is many ways that you can abuse a tag window structure. For example, the string has a length and a maximum length that can also do the same thing, but we didn't want to because talking about tag window structure can be a talk of itself. So we just wanted to talk about one of the very basic techniques of how we've seen this being abused in exploits before. The first step we would like to talk about is how we can allocate the window object from user mode, and that we use create window or create window X. Does any of you guys do C++ programming, window management and stuff like that? So yeah, so these functions should be very familiar to you guys. These are user mode functions, meaning that you can call them from any application in the user mode or from a Windows from a low privilege user, and it will create some structure in kernel without any interaction. And these tag window structures can be freed using the destroy window function. Now, we mentioned that we need specific interesting functions to be able to read and write from objects. In that case, we have the get window long or get window long pointer and the internal get window text. And what they do is actually the get window long pointer reads a specific long at a specific index that is less than CBWind extra from extra bytes, and internal get window text reads a length that is less than or equal to maximum length of the string from string name buffer or pointed to by the buffer. And we have also write data functions like set window long and set window long pointer and anti-user def set text. Now, anti-user def set text is actually a syscall, so you'll need specific instructions to install them or to run it. But it does exactly the same thing, so we can use set window long pointer to write a specific long, which is like, depending on the architecture, can be 4 bytes or 8 bytes at an index that is less than CBWind extra into extra bytes of the window, and anti-user def set text will write up to length, which is less than or equal the maximum length string from the string name buffer. So how can we abuse this? If we think that we have 2 adjacent window objects, we can actually allocate it in memory. We use some kernel bug to corrupt the CBWind extra of the first object. We will be able to read the adjacent window memory functions and members and everything. And thus we will dub the first window as an manager object, which means that we will use this object, the first window, to actually set the pointer from the second window to be able to read and write from any location in kernel memory. So window B will be the worker object. We will use the relative read and write that we gained from the previous memory corruption to actually write into the string name buffer pointer, whatever pointer that we want. And that means that we will use the read and write functions from the string name buffer, would be able to actually read and write from any location in kernel memory. So that was the basic part. It was worth mentioning also at that point that this specific technique was fixed prior to the mitigation that we're going to introduce. But as I said, that we have many ways of abusing tag window structures, and thus why we chose it to be part of the mitigation that Ian is going to discuss later on. Now, after this was abused heavily during 2015, 16, and 17, you name it, somebody, or actually Keen team back in 2015, decided to disclose a bitmap technique, very sneakily to be honest. So they just mentioned it in one slide, but then Nico Economo and Diego Juarez took that mention in 2015 and did a complete analysis and detailed analysis of how can we abuse bitmaps. So bitmaps are images for those of you who don't know, and this is actually allocated in kernel memory. You can do it programmatically, and the bitmap is a very interesting object and was heavily abused in several exploits that we've seen in the wild, and that's why it was chosen as the second most popular choice for object abuse in the kernel. The bitmaps in kernel memory is dubbed surf objects. It has a pool tag, which is in the header of GH5 or GLA5, depending if it was allocated to the look-aside lists or the normal kernel pool. And this is how the bitmap structure looks at the kernel memory level. As you can see, I have highlighted two members as well. One is the sizzle bitmap, which is the width and height of bitmap that is supplied by the user. And the other one is pvscan0, which is a pointer to the bitmap bits in memory. You can allocate bitmaps using a create bitmap function. And you can supply a width, a height, and planes, which actually allows you to control the size of the bitmap being allocated to a specific memory at that time. And then you can free it using delete object. Remember, we talked about getting the kernel memory in their deterministic states using a series of allocations and deallocations, so this will be easily done using these specific functions. Then you can read from the bitmap data using get bitmap bits. So this will read up to sizzle bitmap, which is the width and height of the bitmap, data from the address pointed to by pvscan0. And you can write data using set bitmap bits, which is actually writes up to sizzle bitmap data into an address pointed to by pvscan0. Moving on to the exploitation steps, the same as the window object. Usually you want to get two bitmaps allocated adjacent to each other or near each other in memory, not necessarily following each other. You will corrupt the size member of the first one, which will give you relative read and write. Hopefully you'll be able to read and write up to the pvscan0, which is a pointer member of the second bitmap. And the bitmap A will be the manager object that will be used to set the pointer to read and write from. Later on, we'll use the relative read and write to override the pvscan0 member of the second bitmap and use that as a worker object, and we'll be able to read and write from any point location in memory. Now, this technique was killed in RS3, and everybody was talking about it. And as Dan mentioned, actually, when we were working together at SensePost at the time, I was working on a certain exploit when this technique was killed, and I had to look for a new thing. Which brings us to the palette objects. Palette objects was disclosed by me at DefCon last year, which was interesting. When I worked for Microsoft, I realized that there are many people who knew about this technique before, but yeah. So same again, palette objects are allocated in memory. Palettes are the color palettes for a specific, for anything really. You can allocate it programmatically, and it will have a series of arrays and buffers. So palette entries have a couple of interesting members, actually much more than that, but these are the interesting one for that specific object abuse technique. The first one is the C entries member, which is the number of entry counts that the palette has of colors, so the number of colors that the palette has. And the second one is a P first color, which is a pointer to the first color. And interestingly enough, the allocated colors or the array of colors that the palette has is actually at the end of the object, which is the APAL colors array. So P first color actually points to APAL color. So palette allocation, it's a bit of a hassle to allocate a palette, but we'll go through it. So you have create palette function that takes a logical palette. This logical palette has the palette version, the palette numbers, which is the C entries that we're talking about, and the array of palette entries, which contains the colors that we mentioned. And this is how we can programmatically allocate it from a C program or a C++ program. So this, what we can mention here is that this gives us really precise allocation inside the kernel. So you can actually say this, I want to allocate a palette that is 100 bytes, it will allocate 100 bytes in kernel memory. And then it can also be destroyed using the delete object as well. You can read data, use the get palette entries, which will read up to n entries from an index that the data pointed to by P first color, which allows us very precise reading and writing of kernel memory. And also we have write data. We have actually two functions that allows us to write data to memory using palettes, which is the set palette entries and the animate palette. Both will do the same thing. So it will write up to n entries at a specific index that we supply from data pointed to by P first color. Again, the way that we can abuse it, if we allocate two adjacent or near to each other palette objects in memory, if we corrupt the C entries member of the first one, we'll gain relative and read and write that will allow us to read and write into the adjacent palette, and we can then just use the first palette as a manager and overwrite the P first color pointer and gain arbitrary read and write into kernel memory, and thus be able to move forward with the exploitation. It is worth mentioning that the palette technique has some restrictions. So if you clobber or overwrite any of these members, it will result in a black screen of death, or at minimum, it will result in an error that you will not be able to read and write from. However, this was covered by Sebastian Applet, BitShifter, if you guys know him, and Kozanek, I think, at OffensiveCon, and they managed to work around this technique. Usually when you have arbitrary or relative read and write, you're able to read a lot of data and write a lot of data, which allows you to fix these members when you are working with an exploit. So the next thing I wanted to show you guys, I hope it's working. This is actually the demo that I had from DefCon. It's on Windows 7 SP1, but it will just demo the technique itself. So we're running from a low privilege user. This is a kernel debugger that we're running from the other side. And as you can see on the left side, this is actually the exploit code. So this is a proper exploit. It is an out-of-bounds write in kernel memory. It was already fixed a long time ago. We can see that we allocated a very small object. And then we had a pool layout in a deterministic state. We had our object allocated before a bitmap, and a bitmap has a palette after it. I used it just to demo the technique. GDI object dub is a WinDebug extension that was developed by Diego Juarez. I just had to modify it a little bit because I couldn't find Diego Juarez anymore for some reason. As you can see, I already extended the bitmap size from 1E6 and 1 to 1E6 and 6, which gives me enough memory to read and write from into the next palette. And then I'm able to actually dump the new palette or the original palette at that size, and you will see that the first entries are actually 1E3. So that's the number of entries that this palette can read. After I move forward with my set bitmap bits, I change that to maxed int. So now I'm able to read and write up to 4 gigs of memory from that palette object, from user mode, a very low privilege user. And then after I modify that, I fix the header of the original bitmap, so because I don't want the object to actually do a blue screen of death after I leave. And I modify the pointer for the second palette to look at the first palette, to look at the first bitmap and modify its header. Because if I left the headers clobbered or overflowed, it will actually die after I gain the privileges, which is not something that you want as an attacker. If you want elevation of privileges on some server, and then suddenly the server dies, it means that someone is going to look into it. So this is the clobbered bitmap header. And this is after I write into it, I actually successfully just fixed it into the original one. And then just to show you, the eProcess structure is a structure that is contained in kernel memory for each running process that contains several interesting information. What we're interested in is the token, which shows the privileges of the current process. And here I'm going to steal that process token by relative read and write or by arbitrary read and write using palettes. And then set it to my own exe. And from that point onward, I will just drop into a shell. As you see now, the token for my process has been changed to be exactly like the system process, which means that now I have system privileges. So I successfully elevated my privileges from a low privilege user to system using a simple technique and just using object abuse, not using some magic tricks or anything. For the next part, Ian will talk to us through the death of kernel object abuse and what Microsoft did to actually face that type of attacks and this type of techniques.
Hello, everyone. My name is Ian Kronquist, and today we all live in a world full of vulnerable software, as you heard in the keynote. And there are thousands of developers throughout the world who are introducing new security bugs every day. And we can't fix every bug. And so in the face of this systemic problem, we need a systemic solution, something like mitigations. Mitigations are a way for us to raise the bar against hackers and make exploits and make bugs difficult to turn into exploits or even impossible. Now, at Microsoft, we're fortunate to have a, need to bring this a little closer. We're fortunate to have a historic database of bugs and vulnerabilities. And we've been able to look at what the problems have been in Win32k Windows' graphics drivers, and we found that 23% of these vulnerabilities, of these exploits, have been use after freeze. And this is a relatively simple, homogeneous sort of bug class, which makes it a great target for a mitigation. So when we go ahead and design a mitigation, we need to talk about and think about what the attacker knows and what the attacker can do. And in this case, we assume that the attacker has found a use after free in one of the Win32k objects, which we protect. And they can make this use after free occur at arbitrary times. However, we assume that they do not have an arbitrary write vulnerability. Usually, a use after free is something you use in one of the first steps, which Saif showed you, in order to build an arbitrary write vulnerability. However, we want to make sure that our mitigation is secure in the face of an arbitrary read vulnerability. So that if the attacker can read the data structures within the kernel, they can't, our mitigation will still be secure. Now, I want to point out that not only we assume that we don't have a right, that the attacker doesn't have a write what where, but also we only protect a limited number of types. We do this for some simple software engineering reasons. Our mitigation has some memory overhead, and we don't want to be able to make this change throughout all of Windows and then find it doesn't work for this one type. So we're incrementally rolling this out. Fortunately, with this historic database, we know which objects have been exploited the most, and then we're able to look for patterns in similar objects, which attackers could turn to in the future. It's also important to note that this mitigation does not prevent use after freeze. Since freeze may happen any time after an object has been created, it's really hard to detect them. In fact, to catch every use after free ever, you have to check every pointer access, which is incredibly expensive. And we can't do that in the kernel. So what we need to do is deny the attacker control of memory. If the attacker can control the layout of memory and corrupt these fields, which Saif showed you, then they can control the kernel. So by changing the layout of memory, we can make the kernel harder to exploit if the attacker has a bug. I'm going to talk about two different ways, similar to what Saif just showed you, two different scenarios which we specifically defend against today. The first one is we can't let this happen. We cannot let two objects of different types wind up overlapping each other, where some pointer overlaps with the size, because then they corrupt that pointer, like Saif showed you, and they use it to manipulate some other object, and that's game over. And the other scenario which we need to defend against is if you have the same object overlapping with itself. Perhaps we have something like the palette object, which Saif showed you again, and it's got this APAL color table data, as well as this pointer. And if you manage to get this user-controlled data overlapped with the pointer, and then you change the user-controlled color data to be a valid pointer to somewhere else, you could get all sorts of problems. So we need to make sure that these two objects don't overlap each other at different offsets. However, this is kind of difficult because the palettes and the surface objects, which I showed you, are all in one big allocation, where you have this array at the bottom of the object, and you've got this metadata at the top. And so if all of these objects are different sizes and the attacker can choose how big they want this to be, well, it makes it very hard to make the second case, the second thing which we want to ensure happen. We want to make sure that you can't create a small one of these and then put it where a big one used to be, and then trigger a use after free condition. So what we do is we split up the object. We have this isolated type in this green here, which is just the metadata all the pointers, all the flags, which are in the C palette entry, and then this user-controlled color table, we split up into another allocation which lives on the general heap. So we've got the green stuff, which is the isolated heap, and the blue stuff, which is the general heap. Thank you. And so then I want to show you a little bit about this data structure, how this new allocator, which we designed in order to isolate these objects, really works. So it's a very simple, classic design. We split up this isolated heap into a series of slots. Only palettes can live in this heap. And then we create another distinct heap for, say, surface objects and other types. So then when we want to allocate one of these, we go and we find the first clear bit and find the corresponding empty slot and return the pointer to the user. It's important to note that when we free an object, all of these empty slots are zeroed, so you don't have any old dangling pointers left behind. Thank you. So I'm going to discuss 2 use after free scenarios and then show you what happens when an attacker tries to cause this use after free on the isolated heap and how we manage to stop the attack from proceeding. So we've got some other object over there. It might live on the general purpose heap, and then it points to the palette. And what we're going to do is we're going to free that palette, which is pointed to by the other object, and we're going to forget to update the other object. Maybe there's some complicated mistake. Maybe a programmer refactored the code and forgot about some condition, some edge case. Now we've got this dangling pointer pointing at an empty slot. Fortunately, like I said, when an object is free, the empty slot is replaced with zeros. So now if there was a pointer there, when you try and dereference it via that object, you're going to get a null pointer exception and crash the kernel. Blue screen of death. And then if you try and any of the flags, other metadata has also been reset to 0, which, depending on the design of the object, is hopefully a very safe state. Now I want to discuss another variation on the same theme, kind of the replacement case, and then I'll show you how the replacement case is stopped by this mitigation as well. So once again, we have the same initial state where we've got these palettes, we have the other object, and it points to the palette, and then when you free the palette, we zero the memory, but then we replace it with a different palette this time. Now, it's very hard to go ahead and get that sort of memory corruption scenario which Saif was talking about to happen, because this is a perfectly normal, valid palette. And if all of the palette code is correct and there aren't any weird memory corruption bugs, which is another class of bugs in itself, and we only defend against use after freeze here, the palette will be pointing to a different, the other object will be pointing to a different palette than it originally intended. However, it's just a completely valid, normal palette. So things might get a little weird on the screen and maybe things will jump around, but it'll be, and it's definitely a bug, but it'll be safe. It'll be safe, and the attacker can't use this to escalate privileges. Now, this is actually not a new idea. Adobe Flash introduced heap partitioning in cooperation with Google in 2015, and Internet Explorer had ISOHeap prior to adding a native garbage collector, which nearly stopped all use after freeze for them for quite a while. Shortly after we introduced this type isolation mitigation, WebKit did a very similar thing. So it proves that it's a time-honored, hardened mitigation. It's a great strategy which is being used throughout the industry today. And our work has been tested and validated by both internal pen test teams and external reverse engineering. Notably, Francisco Falcon of Kronquist Lab said, "This definitely eliminates the commodity exploitation technique of using bitmaps as target for limited memory corruptions vulnerabilities. This eliminates that memory corruption vulnerability using the surface object, using those bitmaps, which Saif showed you today. Now, when Saif, when Francisco wrote this blog post about reverse engineering the mitigation I worked on, he said the next thing attackers are going to do is they're going to pivot to the palette type, and they're going to use Saif's technique he presented at DefCon, and they're going to run wild from there. But by the time Francisco wrote his blog post, we already shipped this same mitigation applied to the palette type in insider builds, in flighting builds of Windows. So if you want to see what we're doing, the latest versions of Windows, you can go ahead and do that and run that on your own computer and do reverse engineering to figure out what we're doing right now. So I want to thank you guys and ask if you have any questions. So, sorry, thank you. It's been rolled out as part of Win10. We haven't backported it to older versions of Windows. That's quite a we do that sometimes, but not for like the latest mitigation stuff. And it's turned on by default. You don't need to set it with the advanced threat protection stuff.
So I know that obviously Win10 is a phenomenal shift in security when it comes to non-operating systems.
Yeah.
But a lot of people are still stuck with Win8 and others.
Yeah. Mm-hmm.
UAF is a huge vector.
Yeah.
Is there a chance it's going to get backported to help protect people with older version of Windows?
At this time, I don't know of any plans to backport this work. I don't think it would be the hardest thing in the world to backport. I know I would grit my teeth and do it if I was asked. It's not fun backporting things. And really, the company is very concerned about breaking backwards compatibility. There was actually a performance regression with this code, which I then had to go and fix. So, I don't know that it's going to happen, but it could. I think really Microsoft wants to push Win10 as the future, as the more secure alternative to Windows 7. I hope that answers your question. Does anyone else? Yeah.
When you showed the palette object exploitation, it seemed that the palette objects need to be constructed in a very specific way, and that it's easy to get them clobbered. So, is there any condition that I need for the adjacent palettes so that exploitation can succeed?
So you need to do something called kernel pool spraying, which if you do a lot of allocations and deallocations, you'll be able to get the kernel memory in the deterministic state. Now, there is actually a plan into getting some mitigation into actually making